So we have here the Ethereum 2.0 protocol specification that is in constant development. So let's see things about this protocol specification. So far we are talking about the phase 0 of beacon state. So let's find this beacon chain. You can find here the Ethereum 2.0 phase 0, the beacon chain, and you can find here all the protocol specification that it's talking about how this works under the hood. So you need to deep dive in this specification for understand the things that the BFT problem are dealing for reach the consensus in a safety way and a resilient way. So remember that the consensus needs three main ingredients that are reported in the literature, and the obvious thing is the agreement. That means that all in the network needs to choose the same value. In other words, all the process that decides choose the same value. And the second ingredient of this recipe encodes it's all non-faulty processes eventually decide. The third ingredient for this BFT protocol is the validity. So the common output value is an input value of some process. So far we saw that these three kind of ingredients in this recipe are an extension of the model for reach the consensus in a safety way. So let's see these pool of attestations in the beacon state. So let's move to the beacon state. So far we saw in summary different things here. We saw the genesis in another video, the slug, the for, all the variants that this kind of input has. Then we see that it's based in the story. That means that this is the way to protect the consensus. Then we saw in another video that it's 8-to-1 data that is also called in the proof of work machine, the proof of work chain. Sorry. So this 8-to-1 data is the thing that the beacon state or the beacon chain gets for start growing the chain. So in another video we saw the validator side and also how this balance needs to make in a tuple way of the weight for the int, that in this case the validator register limit. So this kind of object make an interesting way for reach the consensus. And the other thing that we saw, that will be another 4 videos for the rundown, because it's a very specific protocol specification order. It's the randomness, and this randomness is because in distributed algorithms are generally designed with a particular model of the distributed system in mind. So what does mean? Remember that you have the Fisher impossibility, Lasser-Patterson impossibility, that also is called in the LP impossibility. Is that you need to find another deterministic way for the asynchronous network. So cannot be solved deterministical. So this deterministical means that you need to put randomness inputs. So it's an interesting way to see this random, that it's a protocol specification that the proposal is that having hardware specification. So another interesting thing about this beacon state in phase 0 is the slashing condition, but this slashing acts then in the phase 1 when all the validate blocks are start. So this slashing condition is very interesting, and in the literature is not report so good, because this kind of slashing condition is like the thing that decide if the block is a good block or a malicious block. That in the BFT protocol means that are adversaries or not adversaries. So it's an extra protocol specification for protect this kind of protocol. So let's see this attestation for understand the things in the attestation pool. So let's find this epoch attestation in the beacon state. So let us start to think in this attestation pool. So let's start with def is valid a valid slot. So attestation of this slot have what config that is calling the eth2 config. So this will be boolean. Then you need to try validate attestation slot. So the attestation data of this slot will have the current slot, a config that is calling A2 config. So the slot per epoch, that is the protocol specification. You can see here that this epoch slot per epoch is this protocol specification, epoch per slashing, epoch per historical vector. And this protocol specification is because the epoch are the way for connect the slots. So it's a interesting thing for see this protocol specification. And so far we can find here this paper to understand the maths and theorems about this slot per something. So you can find here the first scripts of this protocol specification, and there is a folder about papers here, and this is the paper that make the explication about this epoch per something. So let's download this. Have the paper. So sharing, okay. So we have this condition that is the attestation. The tricky part are the consideration of the delay and the inclusion of the delay. That is something that it's very speculatory because you cannot deal with a random delay of this protocol specification. So far we can see this protocol for each epoch in this page for understand the things. So let's move to see. And we can find here the pocket relation with all the blocks. So in this config you can see that the slot per epoch. So this means that have a relation, an intrinsic relation with the blocks that have this kind of implementation. So far is a justificate chain for following this supermajority height function for reach the consensus in a safety way in this non-deterministic MP harness or MP harness thing. So it's a variant of this MP harness. So let's move to see more code here. So you need to accept you need to see this validation error, return false, else return true. So far this kind of implementation have a class attestation pool. So the operation pool. So you need to pull these for handle a better attestation. So it's an interesting way for handle all the data that you have. So let's move to see how this is work. So this attestation pool will get valid attestation by current slot. So self slot config of this add to those config will be this tuple attestation with the things that this attestation could have. So in this part could be this thing that we saw that is still open in the protocol specification. That is the attestation inclusion delayed and the attestation consideration are delayed. That are things that until now there is not solved for the MP harness because you don't have the random VDF input in a properly way. So basically if you don't have how to will work this in a future, you cannot make this consideration delayed. So this is post implementation. So you need to see how to handle this throughput in the real world scenario. So it's interesting thing, this attestation consideration delay and attestation inclusion delay. And this because it is a experimental code. So let's move to see more code. So this part is still in development, and also it's for make a better performance in this tuple thing. So let's move to see more code. So you need to return the tuple. Remember that it's all about the dealing with the personal asynchronous network. So we have asked for Ezequiel Franzoni, what do you programming? We are talking about the Ethereum 2.0. It's only education, and we are thinking in randomized consensus algorithm. So this is a protocol specification that you can find in the official GitHub repo, and it's interesting thing if you want to start a BFT protocol from scratch, Ezequiel. So for start a BFT protocol from scratch, you need to first make the paper, a very good relate work. If you want to make a kind of different word or different variant of the BFT protocol over there. So we are talking about this kind of implementation right now. So let's move to see more this attestation thing, and you can find the more videos about different protocol specification that this Byzantine fault tolerance protocol has. And so far we saw only the phase 0 right now. So let's move to this return tool. So you have the filter, and the solution of this is the attestation. It's valid slot. If you have any kind of question, you can ask me anything twice, whatever number of attestation that you want to make for wonder things. So let's move to see this attestation thing. So you have the slot and the config, and remember that the config is this A2 config that is very different for the A21 data. So this Ethereum config 2 have a protocol specification, and it's all about to get this randomness thing for the impossibility of fissure. And we saw that this impossibility is the big deal for BFT protocol out there in the partial asynchronous model. So let's see more thing about this. So self this pool storage values. So far we need to get acceptable attestation to finalize this pool. So this is an interesting way for reach the consensus. So if this decorator thing self slot, you have the slot index, so I need to commit this index. So this script is very interesting. Let's see the first script for understand the basically thing. So let's see this first script. So let's find here this first script for the attestation. So we have here different scripts. Let me think a little bit to find a very good example of this principal script. So yes, maybe the beacon chain implementation, because we are now in the phase 0. So let's see this full proof of stake script to find the way for the attestation meaning. Don't expect that this variable could be attestation, because if you start a BFT protocol from scratch, you need to get the first script, then have the compile thing, and then make more paper for the details and the probabilistic way that the implementation could have for the future of the longevity of the network. So this attestation, it's here. You can find here all this about the random and the randomness thing of the VFT protocol implementation. So it's important. So we have here this first Python script that starts talking about this attestation aggregate sync. So this is the first script that compiled the thing from scratch. So in the real world scenario, you need to handle more data because this is a buggy script. I mean, you are only test your first script. So you have here to def get accepted attestation. So it's about this kind of int that are aggregate sync. So let's move to see this this decorate. So this will be a tuple attestation return tuple. So you need to filter this and the set condition that you have here. That is a very good implementation. So the attestation could be have this object. So this could be a beacon block root attestation, the data of the beacon state, and remember that this beacon state have beacon chain, beacon operation, beacon attestation. It's all about the beacon state and how to handle all the data you have. So this need to be a block root of this, and then the slot of attestation, so data slot, then a commit index attestation data the index. Then you need to return all the object, because remember that in Python all is an object, so it's the tricky part. So far you have here all this attestation pool, and you figuring out finally how to make this in a good performance. So you can find here that the first script is only about the attestation aggregate signatures. So you only have this default series, and you start thinking in pool way. So a pool it's a very good strategy for handle a lot of data in a technical way. So let's see the other thing that is the pool, and this will be a class that will be the operation pool. So this is more about for handle a lot of data and how to handle the things that this pool are in operation. So far, let's start thinking in the code of this pool. And let's see that the class of operation pool is a generic tube. So the pool is storage have a root of t. Then you need to think in the first decorating. So you need to solve this, and that will be unknown. Solve the pool storage. So this kind of operation will have interesting tuples here, and it's all about to root and the hash of the tree. So it's very boogie thing for make a good performance in the code that you are trying to type. So we can find here that the first this view the pool doesn't work here because you need to make this first script. So the pool don't have anything to do with the heart of the BFT consensus. Both have the word for handle a lot of data. So it's very difficult to handle a lot of data, because remember that you have all this chain. So this is a beacon genesis, a beacon stay. You're gonna start at this beacon chain, get the 81 data, that is the proof of work chain, then let's start, the chart chain says start, and this genesis state begins for make a good. Then the crosslinks appears, this number attestation starts. So in this way you need to prepare the operation pool of this attestation that needs the pool storage, the instance of the operation of root. You also need the tuples of the transactions of t, that is the input, and you need so far other things that are very interesting how to implement this. So makes sense if you make a backend, or maybe you do databases out there. So there is only the tricky parts of the code for implement only this pool. And finally, this is all about the operation of this implementation, that is the attestation pool that we saw in the protocol specification, that it's about this previous epoch attestation. So let's find a little bit of the scope of this beacon state. How was the implementation in the epoch attestation? So let's find here. And the data star, we can find that the epoch attestation is everywhere. So let's find the first. We saw in another videos the site of the validator. So you can find here that this protocol specification have the previous and the current that are list of this object of the pending attestation with this membership thing of max attestation per slot per epoch. So it's the way for connect this attestation. So let's see here that you have this previous epoch attestation, then the current epoch attestation. So let's find more things about this implementation. You can find that the previous epoch attestation is a tuple because it's a list of the pending attestation and the max attestation per slot per epoch. So you need to be this in the way of the tuple. Then you have this interesting thing in the test. So this is the test. So let's move to the real world scenario. We have here the attestation implementation. We can find here that is in this way. So it's a sample of these beacon state params for handle all the things, and this is very similar for the protocol specification that find here. So it's a copy paste of this. So let's see more things about this previous epoch attestation and current epoch. And remember that you can find here the epoch thing in this figure for understand how this is connected. So we can find that it's a justificate thing, and the epoch is in a specific kind of cut of this chain, and this will be in some way randomness, because if you put a specific number, adversary can attack this with a Python script that decide that in kind of def decorator epoch for this number of blocks you can make I don't know, just thinking the script for this attack. So this could be need to be randomness, so the attacker vector doesn't have effect. This is randomness. So it's the way to protect this protocol specification. So then we have the states. And it's similar, and we can find here the state of this, that is also the copy paste. So you figuring out from the scratch how to put this protocol specification and start make the decorator thing for handle all the objects over there. So you need to return all. Obviously you need to serialize this, but you need to serialize with the protocol specification that is called in the SSZ vector. That is a way for serialize this, then make overrides of this. So it's a interesting way for handle a lot of data. In another videos we will see this specific vector because it's a long spec. We have more here, the current packet attestation and the previous attestation. That is the state of the same thing. Your handle like object, and so far it's all about this and all the operation processing. And you have here the dev process slashing. So let's do think in this protocol specification in the side of handle this process attestation. So let's see this object. So you have this dev process attestation. It's a little bit out of the scope, but it makes sense for understand this beacon state subblock. Where is beacon block? So you have the config, to config. So far it's beacon state, need this condition. And you need to bend this, so you need to do the other part, the ground part, and all the conditions. So this is the basically the first instance for process attestations. So you put the protocol specification, so for the attestation in the block the attestation, you need to validate the attestation that have the input of the state and also the attestation config way. So this proporser is an index of get the vcom proporser index, that is the state, and the config, that is the to config. So far you need to aggregate the bits, the data, the inclusion delay, and the proportion index, and then make the statements that to debugging this and find the correct algorithm for handle this. So my time is over, so let's see in another video more things about this attestation because it's a long spec. It's very hard to understand this code, and it's very hard to figure out a lot of things here. So see you soon.